Okay, so then we should start with the first talk, which is Maria Prusinskaya, and she's going to tell us about SNAD. You're going to tell us what is SNAD. You have 12 minutes.
Thank you. Yeah.
Oh, and I need to change this thing. Sorry. Wait a minute.
Okay. So my name is Maria, and first of all, let me thank the organizers for the opportunity to give this talk. The format of the conference is really great, and I find it very challenging. I'll talk today about SNAD. So SNAD is an international project devoted to anomaly detection problem in astronomical databases and catalogs. Before I'll talk about the project itself, let's talk about the definition of anomaly. So there is a machine definition and there is a human definition. The machine definition is rather simple. Let's say that we have some data. We describe this data with two features, y and x, and we expect that all normal data will be clustered in N1 and in 2 regions, and those that are anomalies could be like some single events like O2 or O1, or they can be clustered in some kind of a small cluster as O3. Human definition is much more complicated because it really depends on your task. For example, if you are working with some catalog or database and you want to make it clean from different kind of the artifacts, artifact can be an anomaly in your case. Or it could be something astrophysically interesting. For example, you're a supernova researcher and you are searching for rare kind of supernova stars. So you could easily call them as anomaly. So human definition really depends on your task and your expertise. In SNAD, as an anomaly, we consider any kind of astrophysically rare objects, could be superluminous supernovae, for example, or kilanovae. And of course, we are hunting for something completely unknown, completely new. Here, I briefly describe our pipeline. So we are working with time series with light curves. Then we describe them with a kind of, let's say, features. And these features, they serve as an input in our machine learning algorithm. As an output, we have some list of outliers ordered by the anomaly scores. And here, there is an important step. Each of those outliers should be scrutinized by a human expert. So we have a team of experts that look at all these outliers by eye. And of course, with the help of some additional follow-up observations, with cross-matching these objects with different catalogs, they try to understand if the outliers, anomalies from the point of view of machine, are interested or not. Those that are extremely interesting, we try to follow up spectroscopically and photometrically, and of course, to publish them. Important step here is that we are trying to introduce the active anomaly approach in our pipeline. What does it mean? So it started as a usual, well, one of the usual anomaly detection algorithm, let's say isolation forest. Isolation forest provide us with a list of outliers, as I said, ordered by the anomaly score. Then we take the one with the highest anomaly score and show it to the human expert. And then human decide, is it interesting or not? Do I want to see more objects like that or not? And provide back its answer to the machine. So if the answer will be no, this kind of objects that are similar to this one in some parameter space, will have a lower importance, and the machine will propose us something else. Below, on these two plots, you could see The fraction of anomalies depending on number of candidates scrutinized by the experts for some synthetic data set, plastic, and for the real data set, open supernova catalog. And you could see that the active approach, which is shown here by green line, is much more efficient than standard isolation forest, which is orange here, or some random sampling. The one good thing about this mechanism, algorithm, is also that it can be used as a targeted transient search. So we tried to use this approach to search for supernovae in Zwicky transient facility data releases. We looked, took 27 million light curves from ZTF and then ran the active anomaly discovery algorithm and ended up with 2,000 outliers. So these 2,000 outliers was scrutinized by human expert. Over these 2,000 objects, we found 100 supernovae stars, half of which were discovered by us for the first time. What is interesting here as well, that 15 of those supernovae were missing in the official alert stream of ZTF. And of course, such kind of loss should not happen. Since the supernovae that we found, they were already archival, so we could not, unfortunately, perform additional spectroscopic observations, but we tried to photometrically classify them by different supernova models. As you could see here at these examples, so the light curves have quite a good quality, and for some of the objects, we have actually very nice rising part. An interesting output of this study was also the discovery of 4 superluminous supernova candidates. One of those candidates, SNAD 160, which is rose here, actually is a nice candidate to pair instability supernovae, a theoretical class of supernovae which is not yet proven observationally. So we were able to obtain some additional spectroscopic observation of the host and to establish its redshift and perform additional modeling to show that it's really very well fitted by pair instability supernova models. Of course, among the anomalies, we found a lot of other non-cataloged objects. Among those, luminous blue variables that can explode as supernovae stars, uncatalogued active galactic nuclears and quasars, red dwarf flares. The activity of red dwarfs, as you know, is very important to study for the question of life at their host planets. And different rare variable stars that we were able to spectroscopically confirm, for example, RS Canum Venaticorum stars. Every year, our team, SNAD team, organizes so-called workshops. And during the last one, so this summer, we also discovered a few very interesting transients. So here you could see a few examples. So the first is a binary microlensing candidate, and another one is an optical counterpart of some radio source. And so to have some fun, of course, among the outliers that is found by the machines, there are a lot of different artifacts. So we store them at snad.spaceart. If you are interested, there are much more. Here, just a few examples are given, so some of them looks really crazy. As my last slide, let me promote a little bit the SNAD ZTF viewer. This is a tool specifically developed to analyze ZTF data. So it was developed to help our experts to study the outliers from the machine. Here you can find the light curves at different pass bands, and there is also a possibility to cross-match this data with different astronomical catalogs and database like Visir, Simbad, Gaia, BSX, TNS, etc. Also, there is an access to FITS images of each photometrical point and Aladdin map. Let me conclude by stressing 2 points. Anomaly detection system must be built for experts, and the definition of anomaly really depends on your task and your domain. So we have to know what we are looking for before we start any anomaly detection. Thank you for your attention.
Well, thanks a lot, Maria, for this very nice talk. So we have time to take a few questions. So let's start with in Paris first. Questions? One here, please, Axel.
Thank you for the very nice talk. I wanted to ask you whether this kind of algorithm could be used like embedded with photometric detection tools, for example, in radio surveys and radio observations where you do have a lot of artifacts and that kind of features. So not to look for the artifact as the object of your research, but not to reduce the number of false detection, for example, in very big radio surveys.
Yeah, of course, you could implement this kind of approach to any time series. So we have GitHub, and there are some instructions how to do that with active anomaly detection approach. And I didn't stress that here, but actually, this active anomaly detection approach really helps us to get rid of the artifacts, because we are not looking for them, and once the machine proposes us an artifact as a kind of outlier, we always say no, and quite soon these artifacts, they disappear completely from the outliers. So yes, active approach can be used to work with some other kind of the data.
Thank you.
Other questions? I have one here from Henry.
Yeah, so just how much active filtering do you need to do this?
What do you mean exactly?
Well, I mean, you're pre-training the model based on some astronomers saying if it's artifact or not an artifact, so how much of that do you need to do?
So for the artifacts, let's say after 10, 15 answers, like 10, 15 loops, machines start to understand that you are basically not interested in. But it's not very easy to answer to that question, because artifacts, well, I show only FITS images
it's
here.
It's great, your FITS page, I already had a look at it.
Yeah, they are of so many kinds, and they produce so different light curves. It could be 1 point up, down. It could be some stochastic spread on the light curve. So
okay.
Really depends on your data.
Thank you very much.
Okay, do we have any questions? Oh, there we have one. And do we have any question on Slack? Not yet? Okay, so we'll pick another one there and then go to New York.
Hi, yeah, very nice talk. My name is Paul Nathan from UCL. You talked about, I think, the number of anomalies that you were passing to the experts. It was around about 2,000 or so. If you were scaling up even further, so that you were actually trying to get, I guess, isolating, if you had like a couple of orders of magnitude more, even in terms of the actual data that you're looking at, have you thought about doing like a second pass so that you end up with maybe, I don't know, the top 20,000 or 200,000, then you run your algorithm again on that set of anomalies to further sort of distill out any sort of meaning or sort of separation between the anomaly types?
So the thing here is that from the early beginning, we define how many outliers can be scrutinized by the experts. So it really depends on the size of the data set and our abilities. So if the data set is not too big, well, it could be like 1% of the most anomalous outliers object. Well, if it is big, it's actually limited by our abilities. So usually we run active anomaly discovery algorithm with a budget of 40, maximum 100 objects, because this is some reasonable number of objects that can be carefully scrutinized by the human who is looking at it right now. So.
Got it. Thank you.
Okay, thanks a lot. So while we go to New York for questions, I'll ask Davide to please come on the stage to prepare for the next talk. New York, do you have questions?
Yeah, do we have any questions in a New York node? Yep.
Thank you. Hi, Mike Wormsley, Toronto. I love the expert in the loop approach. I was interested, you said at the start, how definition of an anomaly depends on what kind of task you're interested in doing. Do you find that your experts rate different anomalies differently? Do they agree or disagree or have different science priorities?
Yeah, so this is an interesting question, and right, so as I said, anomaly definition depends on the expert, and sometimes the expert can be disagree, that's true. So that's why we are trying to scrutinize each data set by, well, several experts, and then to compare, so they're trying to compare their decisions in between and to have a conclusion, okay, well, here probably missed something, this is really interesting, or this is not, so I will change my decision. Because the final goal here is to find something interesting, so there is nothing bad in changing your decision afterwards, after some discussion. But yeah, this is a nice sketch, so we are trying to look at the data by few persons, not only one.
Okay, if there is a last question in New York, otherwise we'll go to the next speaker.
Do we have one more? It looks like we're all set in the New York
Okay,
node.
so thanks a lot again, Maria.
Thank you.